Good morning, everyone. We'll be starting class in 1 to 2 minutes time. Good morning, everyone. And today's lecture is going to be focused on the transfer function realization, which basically gives us an idea how can we represent our Z transform equations into its equivalent block diagram representations. And in particular, there are 4 types of block diagram representations which we're going to discuss in turn, which are going to be the direct form, the canonical form, the cascaded form, and the parallel form. So, right, let's get into this. Afterwards, if we do have time, once we finish the lecture, we'll go back into problem sets 1 and 2 and see about some particular questions that we should do in preparation for the midterm and so forth. If not, if we'll be doing problem set 1 and 2 in particular only on the Wednesday session, so feel free to ask any particular questions during those sessions. And if there's anything you guys are unclear about, make sure and ask during those sessions before the midterm actually occurs next week. Alright, so let's get started. Sorry about that. Let's get started now. Alright, so basically when we have been dealing with our Z transforms and our Fourier transforms, there were so many different ways we can describe the system using different terms or different forms. So the general way we've been doing this so far is by using the transfer function. It's possibly represented by the frequency response. That's if you had a bold plot with a bold magnitude and a bold phase plot response of the system itself. The pole zero arrangement, which is the pole zero graph, which you have already seen in some form or fashion. The impulse response, which we saw in last week's lecture when we were basically talking about the IR and FIR filter responses. And input-output difference equations, which are more familiarly used with the Z transform equations in particular to represent discrete time systems. The one we're going to be looking at today is going to be the block diagram description, which you may have saw with respect to the Laplace transform, but now we're going to have to discuss about it with respect to the Z transform. And typical, any of these designs that you see here, it always starts with some frequency response requirements, meaning that, okay, you need to design a low-pass filter or a high-pass filter with this cutoff frequency, or the system must set the range of frequencies from this frequency to that frequency and so forth. So all these designs here always start with some sort of frequency response requirements. So, and start with that input frequency requirement. You get your h of omega, which is going to be your frequency response of your design system. You apply the filter design here. Yeah, okay. We want to make sure that our system filters out unwanted frequencies and so forth, and it can accept the correct frequencies. We then transfer this into h of z, being that since we're dealing with discretized time systems, we need a z equation to represent this. And then this h of z can be represented back into h of n, a pole zero plot, a difference equation, or a block diagram in particular. So over the next few lectures that we're going to be doing, not next week, but the week after, we're going to be focusing on the input frequency requirement and designing the appropriate filters for discrete time systems accordingly for this input frequency requirement. And in particular, what that means is that we're going to be looking at two different types of filter designs, which are known as the infinite impulse response or IRL filter design and the finite impulse response or FIR filter design. So let's assume that we have some h of z transfer function here. And it's possible for us to get h of n from the h of z accordingly. Question asking how. So it's possible for us to express this in partial fractions and then solve for a and b. And once we get a and b here, we can do the inverse z transform such that we get our h of n equation here accordingly. Then the next question could be, okay, we have the h of n form here. What's going to be the difference equation satisfying h of n? So we want a different form to represent our h of n form here. So we can start back with our transfer function. We can rewrite it such that we have the denominator here going on to the left-hand side, sorry. And then we can expand it out. And then we can take the open form response of this once we expand it out. So remember, the partial fraction form that we just saw was the closed form response. This form here, which we're watching, is referred to as the open form solution or the open form response accordingly. And once we have the open form here, we can basically formulate our difference equation as required. Sorry, not a difference equation. Yeah, the difference equation for h of n, yes. Sorry, that's correct. So this is the difference equation satisfying h of m, but another question could be, what's the input-output difference equation mean that we need to satisfy this with respect to y and x? So we know y of z here is equal to h of z, x of z, so we can remove that h of z component and put in y of z and x of z. We can use the same approach as before, have all the y of n's on one side and all the x of n's on the next side, and y of z's on the one side, x of z's on the next side, and then we can use the open form response to formulate back our terms back into y of n and x of n accordingly. And it's possible that if we substitute this x of n equal to delta of n into this equation, we can get back the h of n equation that we saw in the previous slides. So let's use the input-output difference equation here to actually develop a block diagram that will map y of n being our outputs to x of n being our inputs. So in drawing any block diagram in particular, we always put the inputs on the left and the outputs on the right. So we want to start with our inputs here, x of n on the left. And then we see here that we have an xn minus 1, being that this is a delay. So we cascade those downwards to represent the delay levels. So this horizontal level here will be at x of n or y of n. This next horizontal level here will be at xn minus 1 and yn minus 1 accordingly. And then if we had one more going underneath, it will be at xn minus 2 and yn minus 2. So we watch here that we have an x of n and an x of n minus 1, and we have a y of n and a y of n minus 1. So that means we need to have one delay level on it. In formulating for the x of n's here, we see that for the x of n by itself, this multiplies by 5, so we put in a block here representing that 5. And at the same time, this x of n minus 1 has a multiplication factor of 2. So you put this in for that multiplication factor of 2 here accordingly. We see that the x of n term and the x of n minus 1 term here are joined by a summation series. So we're going to formulate this summation point at some point. But now we're going to focus on the y of n on being our outputs here. So we have y of n and y of n minus 1 here currently. Y of n just only has a magnitude of 1, and y of n minus 1 has a magnitude of 0.8. So we put in this magnitude of 0.8 here going back into our system. And then we connect everything by this summation point here. So this 5x of n plus 2x of n minus 1 adds here. So that covers this part of the equation. And then we need to make sure that this 0.8 y of n minus 1 adds back here accordingly to the result of this. So it goes back to the same summation point. And then the output of the summation point formulates our y of n accordingly. Is anyone unclear about how did we formulate this block diagram? Please indicate so no, because as we go on throughout the lecture, the formulation for the block diagrams are going to get a little more complex. Alright, it doesn't seem like anyone has any questions about the formulation of block diagrams. Oh, okay, let's move on. So the processing sequence for this block diagram. Oh, okay, I got a question here. Alright, nice, let's go back. Alright, so in formulating the block diagram here, remember x of n's will go onto the left hand side representing our inputs, and y of n's here will go onto the right hand side representing our outputs. So the x of n here represents this x of n component, and then we have an x of n minus 1 component representing a delay of 1. So all horizontal levels in this block diagram will represent the current delay level. So this horizontal level here will be at n, and then the next horizontal level underneath will be at n minus 1. This will hold true for x and y accordingly. For our x of n component here, we have a multiplication component of 5, which will be factored in here. So when we go straight across this line, we get our 5x of n. And then for our x of n minus 1 component, we have a multiplication component of 2. So when we go here, meaning that xn minus 1 multiplied by 2 maps back to this here. On our output side, because now we have to factor in y of n and y of n minus 1 here. So we know that this horizontal level here is at n, and this next horizontal level here is at n minus 1. So this is y of n and y of n minus 1. Y of n has a multiplication factor of 1. So if we just have a line here and we don't put in a block, we automatically assume that is a multiplication factor of 1 automatically. And for the y of n minus 1 here, we have a multiplication factor of 0.8. So we put this in here as well. This y of n's here, when we have a delay, it feeds back into the system. Because remember, this is on the right hand side of the equation. So this needs to feed back and then go forward towards formulating our y of n. The addition of each one of these components, so 5x of n, 2 of x of n minus 1, and 0.8 y of n minus 1, can all be connected to one summation series. So this here would be, if we watch the direction here, this is 5x of n plus, and then 2 of x minus 1 plus 0.8 y of n minus 1, and this equates to our output here for y of n, because we have covered all the branches accordingly before we formulate only for the y of n branch here going out. So the summation point here is just representing the additions between each one of these components. So remember, when we formulated this, we have 5x of n, so this branch here is covered. 2 of x n minus 1, meaning this branch here is covered now. Y of n, being our output, is what we're going to be formulating. Y of n minus 1 is this branch here, which is covered as well towards the summation point, and the only branch that is remaining is this branch leading out towards y of n, which gives us our results. Alright, hopefully that clears up some stuff. Any other questions? Oh, these D blocks here are just placeholders. They don't actually represent anything. All this just means is that, okay, these here are just going to go down by 1 delay level. So this here is at n, this one here is n minus 1. You can actually remove these D blocks here accordingly. Alright, so the general trick to this is that you leave the output branch going straight out to y of n as the last part, being this is what you're going to formulate, and then you consider all other branches to formulate the right hand side of the equation. That's your general trick to this. And then if you have anything being an output delay, like y of n minus 1 and y of n minus 2, these feed back into the system. Whereas your inputs x of n and x minus 1 will feed forward into the system instead. And we'll discuss about feedback and feed forward in a little bit as well in this lecture. Alright, let's go on. So for the general processing sequence of this block diagram is that we would have a x of n here being received first, and then the delays haven't actually occurred as yet because we're still at n. So y of n will just be equal to 5 of x of n by itself. And then we then have x of n here being the current state being shifted to the x of n minus 1 state, and the current output being y of n is shifted to the y of n minus 1 state on the next cycle. The new x of n, being our current x of n, will be received, and then the same processing cycle that we just now saw will actually occur, where we have 5x of n here going in, 2 of x of n minus 1 going in here as well, and then 0.8 of y of n minus 1 going in here as well, and the addition of all of these at this summation point going to the output of the summation point gives us our y of n equation as required. Remember that these x of n minus 1 and y of n minus 1 values are stored values because these are past values at the next cycle. At the current cycle, when the system now starts, we'll have x of n and y of n, but we have no storage for x of n minus 1 and y of n minus 1 because we are at that cycle. On the next cycle of the system, we now take that x of n and y of n and we put that into storage, meaning that's going to be x of n minus 1 and y of n minus 1. And then the actual processing sequence that we saw actually occurs to formulate our y of n. So this form of the block diagram here is referred to as the direct form realization of y of n accordingly. And there are other ways to represent these blocks themselves, which you may see like if you're using simulation software like MATLAB and Octave or Simulink, such that you can represent these blocks here with the delays being square blocks and the multiplication factors being triangular blocks. And the summation series will just be a circle indicating where the arrows join if it's positive summations or negative summations altogether. So depending on like the simulation software that you use to represent block diagrams, you may see that the blocks may just have different shapes, but the functionality is just the same as a regular block diagram. So once you have some sort of block diagram representation here, basically using that same strategy we saw in the previous slides, we can basically show how the transfer function is being calculated on a sample by sample basis, step by step, cycle by cycle. So if we go back to our y of z equation here, so this block diagram is represented in z, and we compare the symbols here of the block diagram to the equation, you can see that this 5 here is mapped to this 5. 2 of z minus 1 is mapped here accordingly. This 1 is representing the unity factor, being 1 here for our y of n or y of z. And this 0.8 z to the minus 1 is represented by this 0.8 z to the minus 1. It won't be like, okay, well, hold on, it's negative 0.8 z to the minus 1. But watch this summation series here. The sign inside here is negative, representing this minus part for the 0.8 z to the negative 1. So it's a little bit important to pay attention to the signs of the summation points as well, to indicate, okay, we have 1 here, but we have 0.8 z to the negative 1 here. But this here is minus in front, so we just watch the summation point to make sure that this is minus accordingly. So if you have a generic first order system here, or first order difference equation with no initial conditions, the generic form is given by this equation, where our x of z will have some b0 and b1 z of negative 1. And our y of z here will have 1 plus some a0 z to the minus 1. We can rearrange this equation to make y of z the subject of the formula accordingly as well. And then we can draw up this block diagram just representing this y of z mapping to x of z accordingly. Now another question here would be, okay, we have y of z on the left hand side here, but we have a y of z on the right hand side. Why did we leave this on the right hand side? And the reason why we left this on the right hand side is because we had this z to the minus 1 of y of z. Z to the minus 1 here in the z domain actually represents a delay in z. And we're going to see why we left this here on the right hand side to factor in this delay factor that we just now saw when we were doing this with respect to x of n and y of n. We don't want to be watching this in terms of x of z and y of z. So if we watch our inputs only, we have x of z here being at b0, and this horizontal level here will just be at z to the 0. And then the next horizontal level here will be at z to the minus 1, representing our first delay in our z transfer function. If we had a z to the minus 2, there would be another horizontal level here, factor in this z to the minus 2 delay. And we're going to see that in a little bit when we move on to second order systems. In formulating the equation here, remember we're going to be leaving this line here to be the last line that we process in our block diagram, going straight towards y of z. I'm going to be focusing on all the other lines in our block diagram, starting with the input lines first. So we see we have b naught here for x of z, mapping this part of the equation. We have b1 z to the minus 1, so we see we have a z to the minus 1 here, representing our first delay level, and our b1 factor here. And these here were compounded with x of z, formulating this part here. You see that the b0 x of z and the b1 z to the minus 1 x of z add together, so this will be adding at this summation point. And then we need to focus on the outputs here accordingly. So we have y of z here with a factor of 1, so that's going to be our line here, which we're going to be calculating for. And then we have minus a0 z to the minus 1 of y of z. So y of z is here, feeding back into the system with the z to the minus 1 representing our first delay level, and the multiplicative factor here of minus a0. And then these two parts here, which are added by this summation series being our inputs, need to also add to our first delay level of y of z here. So this goes to another summation series point here. We already have factored in our minus a0 as the multiplication factor, so this can just go straight as a positive summation. And then the addition of all these factors here as a result from these summation points formulate our y of z equation. So just remember when we saw our previous block diagram, when we had x of n and y of n and x of n minus 1 and y of n minus 1, the same thing holds true with the delay levels when we move into the z transform, just that each delay level is represented by z to the minus 1 instead. So this here will be at z to the 0, this level here will be at z to the minus 1, and if we have another delay level, it's going to be at this horizontal level underneath, which will be represented z to the minus 2, which we're going to see in a little bit when we start discussing second order systems. So this form here is also a direct form realization of the transfer function, but this is represented in terms of z. So if we have our second order system here where we're going up to z to the minus 2, and we draw this block diagram out, we see here that typically to represent the next delay level, we just add another z to the minus 1 block here because they will just compound together to make that z to the minus 2. So just for a quick example, we had b2z to the minus 2 x of z. So we start x of z here. So this will be z to the minus 1 x of z multiplied by z to the minus 2 minus 1. So that's going to give us z to the minus 2. That's z to the minus 1 by z to the minus 1 gives us z to the minus 2 multiplied by x of z. And then the multiplication factor here of b2 is formulated at this point. Similarly, for our y of z here, we see that we have z to the minus 1 and z to the minus 1 here, being that we have z to the minus 1 y of z, and then z to the minus 1 multiplied by that to give us z to the minus 2, and then we formulate this here with our a1 accordingly as of such. Now we see here that for a0 and a1, our signs in the block diagram are negative. And you may be wondering, okay, why are these negative? So just keep that in mind. We want to get to that eventually in the lecture as to why those signs here are negative in a little bit. So there are always different configurations for how we go about representing our transfer function, and these are represented based on simulation software or how we actually can implement it physically in hardware. So there are different forms that we need to learn, which are the direct form, which we've basically seen, the canonical form, which is like an optimization of the direct form, the cascade form, which is basically like a serial form connecting blocks together, and the parallel form, which is also another way of connecting blocks together, but to allow for parallel processing in particular. So this structure, when we observe it for our second order system, the left hand side being our inputs is what we refer to as a feed forward structure, which goes towards our output, being y of z. And then for our y of z here on the right hand side, we refer to this as a feedback structure because these feed back towards the input and then goes back towards the output accordingly. Now note for the feedback structure here, our blocks here are minus a0 and minus a1. And the reason for this being is that the direction of flow in the block diagram actually determines the sign of these blocks accordingly. So everything goes from input towards output, meaning that it goes from left to right, straight off. In the block diagrams, everything just goes in one unilateral direction. The blocks here for multiplication factors can remain positive. But once we have something feeding back into our system, meaning that it goes from right to left, the sign of the blocks here must change accordingly for our multiplication factors. So that's why these multiplication factors here are minus, because of the direction of flow in the block diagram. If it goes left to right, these multiplication factors here can remain positive. If it goes right to left because the direction is reversed, these multiplication factors will be negative accordingly. So a feed forward structure, meaning that it goes to left to right accordingly in one unilateral direction, is also referred to as a non-recursive structure, meaning that there's no loops in our structure itself. Everything just goes straight towards the output. And as of such, no past values of y of n or y of z are used to get towards our output. So there's no storage here whatsoever. For any non-recursive structure, it's possible to create a transfer function that can also be used to create something referred to as a finite impulse response or FIR filter, which we're going to be seeing in the next 2 minutes. On the next side of the block diagram, this is a feedback structure, and it's also referred to as a recursive structure because we have loops being formulated here for each one of these cycles. So as a result, we are going to be using past values of the output because of this feedback. And in creating a transfer function for any feedback or recursive structure, the filter that is respectively designed for these are referred to as the infinite impulse response filters or the IR filters, which we'll also be looking at in the next 2 weeks. So a general transfer function is going to be a product of the recursive and non-recursive systems, which we've been seeing so far throughout the entire lecture. Where we can have of some h of z here, map it back into y of z and x of z. We can have the equation here go back to y of z and so forth. We can have some sort of wz factor, where w of z will represent all x of z divided by all the delays. We can evaluate y of z in basically any order when we're doing this. So we can have our x of z's on the left hand side and our y of z's on the right hand side, which we've been seeing and so forth. But one thing I want you to note here for this direction is that watch here that all the y of z's here are feeding forward, but the x of z's here are feeding back. So this is actually going to be a little bit particular. This is going to be a little bit important in particular, because this is actually when we're going to be formulating what we refer to as the canonical form instead. The direct form had us where all our x of z's were feeding forward and our y of z's were feeding back. But in formulating the canonical form here, the x of z's here are going to be feeding back into the system, and the y of z's are going to be feeding forward to the output. Now the reason why we say this is the direct form here is that because we're going to be using this to formulate our cascade form, and this is why you need to pay attention to the direction of the blocks here accordingly in formulating the cascade, or the canonical form. So using that direct form here, and we can cascade our system in any general order, meaning that we can put our inputs to be recursive and our outputs to be non-recursive. Once we use this arrangement here, we can remove one set of delays, because these blocks here are basically repetitive, as we can see. So we can remove one set of delays here and just connect these to the next set of delays here accordingly, getting this nice optimized form representing one set of delays in our system. And this form here is what we refer to as the canonical realization. So just remember the key difference between the direct form and the canonical form, or the direct realization and the canonical realization, is that for the direct form, the inputs feed forward and the outputs feed back. But for the canonical form, it's going to be the reverse. The inputs feed back and our outputs here feed forward in our system. So that's the key difference between the direct and the canonical. And remember, as we just now saw, depending on the direction of flow in our block diagram, I mean if it's going left to right or right to left, if it goes left to right, the multiplication factors here can remain positive. If it goes right to left, because it's a reverse direction, the multiplication factors here are going to be negative, representing each one of these factors here in our transfer function. So remember that key difference when you're dealing with direct and canonical form. So a general work example that we just now did, if we draw it here in canonical realization, this is actually what's going to look like for a general equation as of such. There are other realizations where we can factor this h of z here into a first and second order polynomial. So we have a series of subsystems being multiplied by each other. Once we have a series of subsystems multiplying by each other, this is what we refer to as the cascade form and the cascade representation. So if we have our general first order here, given by our general y of z and x of z equation here accordingly, and we have our second order system here given by this next equation y of z and x of z. In this case, the cascading system will be such that where we have our first order system here going towards the input of our second order system to formulate our output here, y of z. It's basically just a serial connection between subsystems in our overall system, x of z and y of z. So a cascading system is basically used in real-time systems when you need to process stuff sequentially, as well as when you need to minimize the storage requirements, or you have limited storage to process everything in particular. So we need to represent this h of z equation here in canonical representation. It's possible for us to actually do this just by visually watching the diagrams here and just formulating our blocks accordingly. So for example, this y of z here, basically we can see that y of z here and our x of z, we just watch y of z on the numerator here and our x of z being on the denominator. You can see that this 5, 2, and 2 here will map towards the outputs here accordingly. And then there's 1, -0.8, 3, and 7 where we go in back here for x of z accordingly. If we need to sketch this h of z equation here in cascade representation, we need to make sure that we factor the denominator accordingly into multiplication factors. And then we can break this accordingly into a series of subsystems representing each multiplication factor. The next form, and the last form that we need to learn about, is what we refer to as the parallel realization, the parallel form. The parallel form is when you take your transfer function here and you express it into partial fractions or addition of subsystems. So instead of being multiplied together, we have a series of subsystems being added together for a parallel form. And once that you draw this out, basically this means that the blocks here are going to be vertically aligned, meaning that each one of these blocks here are going to be processed at the same point in time accordingly to give us our y of z as required. A parallel system minimizes the processing time, but it means that you need to have more storage requirements to represent all the memory for processing each one of these blocks at the same instance of time. Alright, so that brings us to the end of our transfer function realization lecture. Are there any particular questions at this point in time? A question like this will basically come such that we will give you the transfer function equation, and we will ask you to either sketch the direct form or the canonical form as required. There may be cases where we do give you like a cascade form where we tell you convert it into a parallel form, or we give you a parallel form and we tell you convert this into a cascade form as of such. The conversion between cascade and parallel is actually quite easy because cascades means you just multiply everything together and then you partial fraction it afterwards. If you're doing parallel, you just add everything together, you unify it to one common denominator, and then you break it back into subsystems where they can multiply by each other. The one I'll give you the most trouble would be the canonical form, because like I said, that's where the inputs and outputs directions are reversed. The inputs go into recursive and the outputs go into non-recursive. The direct form is the easiest one to do because that means all the inputs are non-recursive and all the outputs are recursive in nature. So the most tricky one you want to look out for is the canonical form representation. I think in problem set 3 you do get each one of the different forms to look at in particular. But if there's a form missing, eventually when we finish off early in particular and we start reviewing like particular past papers, you'll get some experience with different forms from those past paper questions. Alright, doesn't seem like we have any more questions at this point in time, so let's go back to problem set 1 and focus on one particular type of question that is something surprisingly nobody asks about to do in particular. So I want to highlight this problem here in particular because it's basically the reverse of the convolution. Was it problem set 1? No, sorry, it was in problem set 2. Yes. Let's go into problem set 2. Problem set 2a here. So we're given a convolve signal here, y of n, and then one of the base signals here being h of n, and we need to solve for x of n here accordingly. So this is what we refer to as a reverse convolution problem, where we're given the output and we're given one of the instances of the input here. And we need to figure out, okay, how do we solve for the next input that when we convolve this x of n and h of n here, this gives us our y of n equation. Alright, so let me bring up my whiteboard here. So the first thing that we want to make sure is, okay, we know what's going to be the length of y of n here, because we have this. So this is 1, 2, 3, 4, 5, 6, 7. So we have L of y here, go to 7. And then we have our h here, which was 1, 2, 3, 4. So L of h here was 4. We know in formulating the length for the output of our convolution, the equation for this is going to be L of y equal to L of x plus L of h minus 1. And we're going to be trying to solve for L of x here accordingly. So there's going to be 7 equals to L of x plus 4, 1, and L of x here is going to be equal to 4. So meaning that for our x vector here for our convolution, we know that it must be only 4 values. So we have our y of n signal here, our h of n signal here, and we can just basically formulate a convolution table to say, okay, we have the output here, and we have one of the inputs. Let's use the convolution table in reverse to solve for x of n accordingly. So let's draw a convolution table here. And let's put h of n signal here. So this was 7, 1, 9, 8. And we know we had, for x of n signal, this must only have 4 values in that vector. So we'll call this x1, x2, x3, and x4. And I'm just going to write y of n here for for quick accessibility. So 4940 40 56 39 60 32. Okay. Alright, so we know that when we're summing across the anti-diagonals, we're going like this, 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 and then this, right? Meaning that each one of these anti-diagonals here will give us a term for y of n. So the first anti-diagonal here in particular, we can watch this here, and this is going to be 7x of 1 equals to the first term in y of n. So this here is 7x of 1 is equal to our first term in y of n. So y of 1. And 7x of 1 here is equal to 14, meaning that x of 1 here is going to be equal to 2. We can then use the second anti-diagonal here, being this one here, to formulate for our second term here, y of 2. So in this case, let's watch convolution table. We have 1 of x of 1 plus 7 of x of 2 here equals to y2, which is 9. So this is going to be x of 1 plus 7x of 2 equal to y of 2. X of 1 plus 7x of 2 equal 9. And we just now solve for x of 1 here. X of 1 was 2. There's 2 plus 7x of 2 here equal to 9. X of 2 here equal to 1. And we can keep on going, but there's a very nice optimized way to go about solving this. So we know x of n had 4 values here. Just use the next side of the anti-diagonals here to solve for the other 2 values. So this last anti-diagonal here, so this is 1, 2, 3, 4, 5, 6, 7. 7, right? This last anti-diagonal here gives us y of 7. So this here is going to be 8x of 4 here. It's going to give us 32. 8x of 4 here equal to y of 7. 8 of 4 is equal to 32. X of 4 here will be equal to 4. And then that takes care of this anti-diagonal. And then we can use this anti-diagonal here, summation of these 2 terms here, to solve for x of 3. So this here will give us 8x of 3 plus 9x of 4 is going to be equal to y of 6, which is 60. This here, 8x of 3 plus 9x of 4 is equal to y of 6. 8x of 3 plus x of 4 is equal to 60. Substituting x of 4 here, which was basically 4. This here is going to become x8 of 3 plus 10 by 4 is 36. 60. X of 3 here is equal to 3. So as a result, because now we have our x1 to x4 terms, x of n here is equal, we're going to watch each one of these terms, 2, 1, x of 3, 3, and 4. 2, 1, 3, 4. And that basically brings us to the end of a deconvolution question. So once you encounter this particular type of question here, where you're given a convolved signal y of n accordingly, being that's the output of the convolution, and one of the base signals here being one of the inputs here being x of n or h of n, the deconvolution process will be where you need to solve for the next base signal, where you're given the convolution here in particular. So the process I just now showed you was how to go about doing the deconvolution process to solve for x of n here in particular. So remember, you need to start with figuring out what's going to be the length of x of n, and then use the convolution table in reverse to solve for x of n. Alright. So any particular questions about the deconvolution process? It doesn't seem like we have any further questions regarding the deconvolution process. Alright, so on Wednesday's session, we're going to be focusing more on problems from problem sets 2A and 2B in particular, as well as the problems that you can be expecting to come on the midterm as well. So these will give you a nice general preparation for what you're going to be expecting next week, Wednesday, for the midterm and as of such. And like I said, during that Wednesday session, if you're unclear about anything in particular, ask your questions while we're doing stuff, so that way you can make sure you can know how to go about solving these problems in particular and whatnot. Just remember that for the midterm, the marks that are assigned on the midterm are heavily weighted towards the approach and the working that you do. So the final answer will just be like only worth 1 mark out of the entire 20 marks for the question or something like that. The remaining 19 marks are going to be heavily weighted on the approach and on the working. So it is very important to show all steps in your approach, as well as to show all working on your paper that you're going to be writing on in particular. For some people who do have like graphical tablets or touch screens and so forth, for the midterm you are allowed to like write your solutions using OneNote or some other form of digitization, so long as it's handwritten solutions only. Typewritten solutions will not be accepted. I'll eventually post up instructions on the forum reiterating this, where you will be allowed to use your stylus to write your solutions using OneNote and so forth, and then you can PDF it afterwards to submit your stuff, instead of having to write on paper with ink and so forth. But if you don't have access to a stylus and whatnot, paper on ink and just taking photographs are still acceptable regardless. Alright, so until Wednesday, take care, be safe, and I will see you guys soon. Later. I'm still working on a time limit for the midterm, but it would be somewhere between, I would like to say between 6 and 12 hours. But I will let you guys know all the details in a forum post very soon. Alright, see you guys later.